All right, hopefully we are now live on YouTube. Bear with us as this is our first time running a live stream, but I'm seeing that there are a few people watching, so hopefully it's all good. All right, we're live. Welcome everyone. This is our first live stream, and today I'm joined by Amir, who is joining us from Mixed-Bread AI. So first of all, I think we'll start with some brief introductions. And we're going to be talking about how Mixed-Bread and the company that I work for, DeepSet, collaborated in training a German embedding model. I'm just going to give a couple of maybe another minute to let people stream in. And while that's happening, I'll just start by introducing myself. So my name is Tuana. I work in the developer relations team at DeepSet. I focus on Haystack, which is our open source AI framework. And Amir, would you like to tell us a bit about yourself?
Yeah, so I'm one of the co-founders of Mixed-Bread and leading the ML effort in our team.
Nice. All right, so let's start. A quick intro into how this live stream is going to go. So a couple of weeks ago, the 18th of July to be specific, DeepSet and Mixed-Bread released a new German-English embedding model. So we're going to give a quick introduction to that. I'll just quickly share with you the announcement article, some statistics about the model, what the model is based on. We'll also share with you how you can get started with this model. But then I'm going to be handing over to Amir, who's going to discuss how the model was trained. So we used binary quantization and MRL. So we're going to discuss what those are, how they help the model. We'll also discuss briefly how the model was evaluated. But I think the main chunk of this live stream is going to be an AMA. So please feel free to drop in your questions. Once Amir is done, we'll ask a few questions to him. We might not cover the whole hour, but yeah, we'll go as far as we have to answer all of your questions. All right, so the model that we released, DeepSet Mixed-Bread Embed DE Large V1, is based on multilingual E5 large. It is open source too. So in a bit, I'll show you where you can get to the model card on Hugging Face. And you can use it with a lot of tools. So you can use it with sentence transformers, Haystack, and so on. It was fine-tuned on quite a lot of pairs of German data, and it was specifically trained for RAG, or specifically retrieval for RAG. If you are interested, the model was benchmarked on quite a lot of data sets, and that QR code over there, I think we'll drop in the link as well in a bit. That QR code will take you to the spreadsheet, including all of the benchmarks, which is on top of some very common data sets that you may have seen already, but it also includes some data sets from the DeepSet customer base within the legal and newspaper realm. So if you are interested, please do check out the benchmarks. I'll also quickly show you how you can start using this model. So the model can be used with Haystack, with the sentence transformers integration, as well as the Mixed-Bread integration. We'll be sharing with everyone this collab, which will show you how you can use the embedding model. Let's scroll down. For example, a very simple indexing pipeline. Here we're indexing. I just copied these over today. These are paragraphs from news articles about the Olympics in German. I think they are literally today. This shows you how you can use the model to embed your own data, your own documents, using the release model into an in-memory document store. You can also inspect exactly what your pipeline is doing. So in this case, we are using the sentence transformers embedder with our model and writing it to an in-memory document store. The other thing that this collab is showing you is how you can use it with the Mixed-Bread AI integration for Haystack specifically, which is pretty cool because you can also opt for using binary quantization. So we're going to share this with you in a bit. All right. So if you would like to, you can scan any of these QR codes. That's going to take you to the full announcement of the model card, the Mixed-Bread Haystack integration. We'll drop those links in the comments anyway. But without further ado, I think, Amir, I will hand over the stage to you and start learning about how you train this model.
Yeah, thank you, Tuana, for the lovely introduction, and thank you for hosting this and organizing this. So, welcome everyone. So, I will talk a bit about how we train this really delicious embedding model together with DeepSet. So, before we jump in, just some small words about MixPred, if you're not familiar with. We do search, we do information retrieval, and push the state of the art, especially with open source. Our models are downloaded over 7 million times on Hugging Face and come with novel compression methods, so you can scale up your systems, and they're widely used in production and pushed as the state of the art, like we did with DeepSet this time. So cool. Let's jump into it. So let's look at the classical RAG pipeline, right? So we normally have a data source and we do search on top of that, and then we put it into an LLM, and this response is then fed to a user or to an application. And the most crucial part is the R in RAG, the retrieval step, which I call it here search. And if you think about it, when you normally do search, for example, in your Windows Explorer or Mac OS, you type in something and find documents which are relevant. And for this, normally classical approaches are used, like keyword search or sparse search. And what happens there is, for example, my brother's selling trains, and if he would search for train, he would just match documents where the word train is really occurring. So what if he wants to also find documents where you have words like railway or subway, which are also relevant to this term? So you couldn't really find them with this traditional approach. Another issue is that you have ambiguous words. So for example, if you search for apple, like the fruit, whereas apple the brand, how does the model really knows or your system really knows what to find here? And also an issue of this classical approach is you can't look to the neighbor words. So for example, if you're searching for not apple, the model wouldn't really understand this. So the word order is not preserved. And also you have issues for abbreviations like reg versus retrieval augmentation and a lot of more issues of them. And here, as the dense representation or embedding models come to our rescue. What we want to achieve with those models is just to have a mapping function where we put in some information like text and get out an embedding vector or a mathematical representation of this information. And the trick here is that this function or model should map the text objects like this, that relevant objects are laying closely together the mathematical space. So how it would work is you put in bread is amazing, or in German this time Brot ist großartig, and get out an n-dimensional vector, and this time 1024. If you put in a second term like Brot schmeckt super, means bread tastes fantastic, you will get out a second vector. And because they're talking about how a great bread is, they will lay together closely in the vector space. So, but unfortunately, most state-of-the-art model or really good models and open source models, they're trained on English data and also have language bias. Language bias means if I ask questions, for example, about things in German, for example, who's the president or where's the president, it will still match it likely to, for example, Joe Biden, because it was trained on large majority of English data. And this is really unfortunate if you really want to go into production with those models like DeepSet's customers. And here, DeepSet and MixPred came together to fix those issues for the German language and provide an open source state-of-the-art model, which comes with a lot of cool tricks. It was trained, first of all, for with vast majority of modern compression method, so you can scale up those systems. And they were also trained for production readiness in mind. So meaning here DeepSet's expertise from their customers and clients came in to really think about how we can retrain them so a lot of people can use them in production. But for talking a bit more how this model was trained, I would like to give a gentle introduction how embedding models are trained in general and what they try to achieve with these training methodologies. So how those data sets are normally constructed is you have an anchor or an anchor, could be a query, or an interpositive, which could be an answer to this query. Or if you think about a news article, you have a heading and a paragraph where you they are relevant to each other, and you have paper, titles, and abstract. So you have those anchors and you have those positives. And what you want to achieve in the Latin space is that positive and anchors are laid closely to each other, while the negatives are further away. And those negatives are constructed either by using in-batch negatives, so meaning if I choose, like, for example, 100 question-answer pairs and look at question-answer pair number 1, I treat the rest as negatives. So I want to push them further away, while I try to make the positive pair closer to the anchor. So that's how we normally train those embedding models. And by doing this, we would try to teach the model to understand the real world and understand what's really relevant. So, and the most important part is here to get high quality negatives. So meaning if you get really good hard negatives, meaning where the model has issues or issues to really understand, if it's further away or closer to that, it will learn a better representation of those informations. So how was this? So now you know in general how those models are trained. And I like to talk specifically how this model was trained here. So we start with a really, really powerful and extremely good model for multilingual data, the infloat multilingual E5 large data, to save compute resources and also not gather too much data, because it's extremely hard to gather high quality data. And we scraped over on top of that or gathered 30 million pairs of high quality German data. And here we had a mixture of just query answer pairs, like meaning just anchor and positive, but also triplets, meaning anchor, positive, and negative pairs. And what's super important for us is that we have absolutely no overlap with the test benchmark here. Because if you think about it, if those models doesn't generalize well, because go back to this, how they are trained, right? So if they never see data before, where to put those data points in the Latin space, and you put in new data, they have to guess where to put it in. It's basically a shot in the dark. And if they never saw this before, they will have a hard time to really do that. So to really test how they work in real-life settings, where we normally don't know how the data distribution of customers or clients look like, we really wanted to have no overlap with test benchmarks so we can assess the real-life performance of that. And one trick we did here as well was we used LoRa training for query positive pairs and full fine-tuning for triplets. So once we trained those models, here the expertise of DeepSet helped us a lot. So DeepSet has a lot of different customers in a lot of different domains. And so for us, as I stated before, it was really important to train so it works in production and real life use cases and not just top on benchmarks. So as I mentioned, we trained with 30 million pairs across a lot of diverse domains and variety real world samples, and then did a case study with one of the customers of DeepSet, which was a legal client. And here we tested our model versus a fine-tuned model for specifically the domain, Voyage Law 2. As we can see, our model outperforms the one of Voyage quite clearly, which shows that it's really working well on real-life cases. So another thing DeepSet also encounters once they go with their customers in production is that once you want to scale up those systems, it gets super expensive. If you think about it, it's just really like mathematical representation of information with a lot of vectors, and they take a lot of storage. So I think I'm cut out a bit always, so like this. Cool. So if you would want to store a lot of this information in a vector database, for example, in AWS, this costs a lot. Let's take a look at an example. So our model puts out 1024 dimensions. And if you want to store 1 million embeddings, this would cost you around $1,500 per month for just storing them. If you go further in the scale, you get to 200 million, 50 million vectors. This costs you like around $3,600. And for 1 billion embeddings, you are already at around $14.5 thousand. So we need a way to reduce this memory footprint, because if you think about logs or e-commerce use cases and so on and so forth, 1 billion is not so much. So, and here embedding compression comes in, and there are different type of embedding compressions. But what all want to achieve is want to make it cheaper to store those embeddings. And another side effect is that it's also faster to retrieve if you search over compressed embeddings. And there are different type of compressions. One is, for example, binary quantization. Here we do the following. So normally every embedding has 32 bits if it's stored naively. and we compress it down to 1 bit per dimension. So meaning that you have 32 times storage saving. Another one is Matryoshka representation learning. Here you basically just truncate the information. So instead, when our model has 1024 dimensions, we just take, for example, the first 512, the first 256, and so on and so forth. Or if you want to be fancy, like we are, you do binary Matryoshka representation learning, means you just combine both and get like even more storage saving. And there are also several other quantization methods, which I don't want to talk in depth. For example, int8 or int4 and so on and so forth. But you should just try it out. Our model should work on them also pretty nicely. So let's talk a bit about more Matryoshka representation learning. This sample is taken from the Hugging Face blog. So what happens is, so if you put in an input like it's so sunny outside, here it should be German, but our model also works pretty well on English, so it's German-English data. It was trained on German-English data. So you put it into the Matryoshka representation model, and you get out a vector of 1024 dimensions. What you can do now, that's the Matryoshka, if you think about it, if you big Matryoshka likes the whole embeddings, then you go smaller, smaller, smaller. You can just truncate this vector into 512, 256, 128, and 64. And the model will still perform really, really well on that because it was trained like this to store a lot of information, for example, in the first dimensions, to enforce that you can later do Matryoshka. And if you want to have more and more performance, or you care about performance for your use cases, you just use larger vectors. And about binary quantization, so as I was mentioning, so a vector, so those vectors are normally in data type float 32, meaning you have for every dimension 32 bits. And what you do is you just go down to 1 bit by doing simple thresholding, meaning if the value at the dimension 0 is larger than 0, then you put a 1, as you do 0, and then you go over all the dimensions. This allows you to have 32 times less memory, which directly translates into 30 times cost savings and 40 times faster retrieval. So how is this faster retrieval achieved? So normally, if you do similarity matching, like cosine similarity or dot product, you just have a vector multiplication and some normalization only over it. But for Hamming distance, which is really expensive for CPUs, but for Hamming distance, it's just 2 CPU cycles, pop count and XOR. So meaning you can really go over and have 40 times faster retrieval because all modern CPU architectures are supporting those operations. So, but to really do that nicely in production, you need a model which is trained with compression awareness, like this model. And as I mentioned, you can be fancy and combine both of them, meaning you do Matryoshka first, for example, truncating it down to 512, and then do binary on top, which means you can get up to 64 times saving cost and still over 40 times faster retrieval while maintaining 90% of the performance, as we showcase here. So the performance goes slightly down, but it's still around 90% of the performance. And what you can do to counter measure this effect or do counter effect to this is you retrieve more documents, like 1,000, and then put it into a re-ranking model, which also one is coming up soon, hopefully, with DeepSet and MixSpread, where you can then just re-rank and get still good performance. So you don't have this hard of a performance hit if those 10% are too expensive for you. And let's talk a bit about cost here. So we know, okay, it's fast. You have a lot of, still have good performance, but what does it mean in numbers for cost savings? So if you would store with float 32, as I mentioned, 1024 embeddings, this would cost you around $14,500. If we go down to binary, we can cut this cost down instantly to $453 only for storing 1 billion embeddings. And if we want to do it even fancier, as I mentioned with Binary MRL, we can even just cut it down to $226 per month. So going down from $14,500 to $226, and they can just lay in memory, so you get fast retrieval and just use it in production. So I think this was really important here because, as I mentioned, DeepSet has also customers which they want to scale up those systems, and also having such cheap embeddings and new representation of information enables new use cases at larger scale on unstructured data. So cool. That's all I have. As I want to say, we wanted to put a bit more time on to ask me anything and questions. So happy to answer questions.
Thank you. Hopefully you can hear me. Let me know if you cannot hear me.
I can hear you.
Yeah, great. All right. Thank you very much, Amir. So from this point on, it's really going to be about chatting about the model. I have some questions ready from my side. If you do have any questions, I've seen a few come in. We'll definitely show those and ask Amir as well. So if you do have questions, please drop them in the comments and we'll get to them at some point. All right, thank you very much. So I didn't know too much about binary quantization or MRL, so now I feel a bit more educated. But one of the first questions that I jotted down was any tips on how to decide on the trade-off of using binary quantization versus MRL or both, because you made the decision to use both. Especially because my understanding is for binary quantization, this is something that you can decide to use post-training, whereas MRL is something that you do during training.
Yeah, exactly. So I think there are like two considerations. We wanted to give the users all flexibility to do whatever suits best their use case, because we didn't see too much of a performance hit doing all those optimizations. And one thing to think about is, so for binary quantization, you need also vector databases or a store which supports Hamming distance. So meaning you just can't throw it in and use it. So you need something which supports that. And that's getting more and more common, that vector databases, Postgres, and search engines are supporting this, while Matryoshka can be used out of the box with basically everything which supports vector search. So we wanted to give the users the flexibility to decide what makes sense for them and just use it. And practical consideration is like, I'm a big fan of binary quantization because it seems to really work well. You get also the faster retrieval times and so on and so forth. But if your vector database is not supporting that, use Matryoshka representation learning, and you have insanely large scales and a combination of both. I think is the way to go.
Nice. I think I will also try to bring in something from the audience. Hopefully this works. Let's see. All right. Did you use some framework, for example, sentence transformers for pre-training, fine-tuning, or is it purely your own code?
Yeah, so we used our own code because we have some internal training frameworks which are really nice for quickly experimenting and some other stuff. So we use our own code, but Sentence Transformers has extremely good support for all the stuff I mentioned. So you can just go ahead and use it as well. And I think Sentence Transformers, Tom, correct me if I'm wrong, you're also here, right? They also support multi-GPU training now, so it makes a lot of sense to use it as well.
Actually, Tom has basically the same question that I had also noted, so I'm actually going to show his question now. Why did you use LoRa for pairs? What was your motivation? Faster training? Did you evaluate the performance with and without LoRa?
So yeah, sure. As I mentioned, for people who doesn't know what LoRa is, low rank adaptation, which means you don't train the whole model. Instead, you just train some layers of that. And as I mentioned in the talk, we just started with a really strong base model, the multilingual E5 large. And what we figured out is that when we trained it with just the query answer pairs without explicit triplets, we had a lot of noise in the in-batch negatives. So instead of so what we found that LoRa helped us to cut through this noise and makes the model more generalizable. That was the idea. It was not really about faster training, but it was a bit that the noise doesn't have enough, too much influence on the model, but we still learn from this data and push it into the right direction. And yes, we evaluated the performance with and without LoRa. We find that with LoRa, it generalizes better and just generally performs better on our benchmarks.
All right, I think I'm gonna ask one more question from the audience, and then we'll go back to some of my own, and then we'll go back to the audience again. What about tokenizers for the model? Was there any tuning?
So we use from the multilingual E5 large model, which is from XML Roberta, the tokenizer. What we did to save a bit memory footprint and also storage, we throw away all non-Latin tokens, meaning Chinese, Arabic, and so on and so forth. Just keep like the one commonly used in English language, in German language, but also in French language, so with Latin alphabets. This was the optimization we did, but we didn't train our tokenizers ourselves because we figured out that it works pretty well as well on all our data. We did a small experiment with that.
Cool. And here is the main two questions on my side, I feel. So this model was trained for RAG, retrieval specifically. Can you use it for anything else? Have you tried to use it for anything else like classification, clustering, etc.?
Yeah, sure. So the model was really with retrieval in mind because, as we say, we work close together for DeepSet, also with our customers and so on. So, and most use cases there are retrieval, but the models should also work pretty well on clustering and classification. But we haven't specifically benchmarked it, but I think the community would love to test it, and we would love to hear about that. So, what you guys can do with that, but it should work for it as well.
So if you do benchmark it, please let us know. We'd be interested to know. How much did the English performance suffer after fine-tuning for German?
It was actually better because we also included German English press as well, so it performs better. So we did a small benchmark because the clear focus was on German, but on the English benchmarks we tested, it performed better than the multilingual E5 model. So you should also see a boost in cross-lingual, but also on English retrieval and also German retrieval.
Nice. All right. So we have quite a few more questions coming in. So I'm going to start showing them, and then we can have a read through them together. How did you ensure binary quantization performance?
Yeah, so it was a mixture of angel loss and embed negatives. So who is not aware of angel loss? There's a paper written by our really fantastic colleague Sean. I'll give it a read, as that's how we mostly train our models. But we also did some tricks to infer information for quantization awareness after training to just be ensure that the model understands that. And there are some papers, I can't go too much into detail, but there are a lot of papers about how you can do binarization post-training and also how you can ensure, for example, that the gradient still exists, because the issue with binarization is, right, you don't have continuous values anymore, so you don't get a gradient. So you need to do some tricks to still have a gradient and do those optimizations.
If there is anyone in the audience who has these papers at hand or can drop links in, I think everyone would appreciate that. So I think Bilge, Tom, Stefan are all in the stream. So if you do want to share some educational links, I think we'd all appreciate that. All right, so I did actually miss, there was one viewer who asked two questions back to back, and I starred them and I forgot to actually share with them. How does distillation compare with truncation MRL in terms of quality? And there's a follow-up to this.
Let me understand the question first. What does this? What does it mean? I'm not.
Maybe you could clarify in the comments if you would like to clarify further, and we'll bring this question back up once you do. I think maybe, do you prioritize in any way which dimensions you truncate out? Like, can you do something like PCA in that case? This was the follow-up, if that helps.
Exactly. That's a bit different, PCA, so where you try to figure out which dimensions are relevant. No, so here you really enforce, so the users has the flexibility to just truncate it. That's most information are just laid in the first dimensions. So you just train it with this loss in mind. So it's not really saying, hey, let's use a vector 200 dimension 256, 512, 7, and 8. So that's not what we're doing. We just enforce the information to be in the first dimensions. I can really recommend to read the paper about it. It's a really, really good paper. So if someone has it at hand, please post.
Yeah. All right. I think there's one last question from me to end all of the questions. Maybe no.
There's some still in the chat, for about the, did you use knowledge distillation from cross-encoder?
Oh, I'm not seeing that. If you're seeing that, maybe if Bilge or someone can bring that up. Where is this?
From Stanislav. Okay.
Oh, yeah. Okay. This one.
Yeah.
There we are.
So we didn't do knowledge distillation from cross-encoders because you need a good cross-encoder before you can do that, right? So this would be the next step actually for us. So I think Tuana wanted to ask that, so I can talk a bit more later, but in short, we didn't do that yet, but this could be an interesting next direction. Also, for example, using LLM rankings as signals to figure out the right ranking for those models. I think this could be also a really, really interesting direction, because what we figured out right now is that the model is really good in answering those questions. But if you have multiple positive pairs or positive passages which are relevant for these queries, the ranking is sometimes a bit mixed up. But this could be interesting feedback signals from cross-encoders or LLMs to solve those issues.
We have more coming, so it's not going to end anytime soon. There you go. Which batch size did you use with the in-batch negatives? Some papers use huge values, but I'm curious what you used. There's a follow-up. Did you mine hard negatives?
Okay, so I'm not aware, so I don't remember the right number at the moment, but I can look it up and happy to share it afterwards. So I can maybe add it into our blog post, so this should come up during the day. So sorry to not really answering this, but not as huge as, for example, the E5 paper, because as soon as you have really nice triplets, you don't need a super big batch size, but a big batch size still helps. Yeah. And regarding the mining hard negatives, yes, we did. I think that's the most crucial part for us, at least, so how we train the models. And what was done was a combination of classical approaches like doing BM25, but also some novel approaches using feedback data and so on and so forth to mine those negatives.
Next plans. Are there any next plans?
Yeah, exactly. So as I was mentioning all the time, so re-ranking is still a good open source multilingual data. Multilingual model is missing, so we want to train one on German as well, together with DeepSet, and that's like the current plan. And let's see what maybe a version 2 of this model and some other cool stuff coming soon as well, which will help Haystack users or DeepSet users to enhance their retrieval performance for RAG.
All right. Thank you very much, Amish. And I've been working in the AI space for a while, but model training is definitely something that I am not accustomed to in the last few years. So this was quite educational. Thanks very much. And for everyone still watching, if you do have any final questions, please let us know. I think we've spotted one other. Amir, are you seeing another question?
Yeah, clarifying the previous question, I was wondering about ways to reach a small model, whether you compared with distillation with some things that could work, we tried. Yeah, so we haven't played too much around with distillation, but this model is amazing. It's Apache 2.0, so you guys can go ahead and basically use sentence transformers to distill it. We haven't tried it, but this could be also something we could do in the future. But I think we know from other people who distilled our English model into a smaller one, and it worked really, really well. So this should also be the case for this model. So feel free and go ahead and please share with the community.
Thank you. And I guess I'm going to end this stream by asking everyone whether you enjoy these types of live streams. Like I said in the beginning, this is the first time we're running this. So if you do enjoy this type of thing, please do let us know in the comments. And with that, thank you very much for joining. Thank you for being the first victim of a Haystack live stream, Amish. This was very enjoyable. And for everyone who's wondering, hopefully this has recorded, so we will be uploading the whole stream to YouTube, to the Haystack channel, and we'll share that around on social media. You can find both myself and Amir on LinkedIn, Twitter, everywhere, basically. So please do keep in touch. And thanks for joining our first live stream.
Yeah,
thank you, everyone.